Viewers, welcome to today's episode. Today we want to consider mathematical induction. When we have a mathematical statement that is true for all natural number n equals 1, 2, 3, ... like it continues, it is not possible to verify this statement using a step-by-step method because we have an infinite number of cases to verify and it can never finish. So the principle of mathematical induction is a very useful and powerful tool that we can use to verify the mathematical statements. Suppose that we have a mathematical statement Pn equals 1 over 1 multiplied by 2 plus 1 over 2 multiplied by 3 plus ... plus 1 over n into n plus 1 equals to n over n plus 1. Now, this mathematical statement is true for all natural number n, but we cannot start verifying this mathematical statement using a case-by-case method. So that is why we need the principle of mathematical induction. So the first step in principle of mathematical induction is to check the truth of Pn for n equals to 1. That is, you want to check to show that P1 is true for n equals to 1. Then the step 2 is to check the truth of Pk. We use an inductive hypothesis to assume that Pk is true for n equals to k. Then step 3, from the step 2, we can show that Pk plus 1 is also true. So it means that the first step of mathematical induction is called the basis of induction, which is for us to check if the statement Pn is true for n equals to 1. The second step, an inductive hypothesis that Pn is true for n equals to k. Then finally, from the step 2, that is from the step 2 of Pn is true for n equals to k, we can then show that it is also true for n equals to k plus 1. Now let us take this an example. They prove by mathematical induction that 1 plus 3 plus 5 plus ... plus 2n minus 1 equals to n squared is valid. The solution goes thus. We are given this mathematical statement 1 plus 3 plus 5 plus ... plus 2n minus 1 equals to n squared. All we need to do is to verify this mathematical statement for n equals to 1, for n equals to k, Then from that statement from n equals to k, we can then show that it is true for n equals to k plus 1. So let us start. The left hand side of this equation here is 2n minus 1, and the right hand side is equals to n squared. Because if we put n equals to 1, the right hand side must be equal to the left hand side. And if it is not equal, it means that the mathematical statement is not true. So let us see if it will be true. Is it true for n equals to 1? We have the left hand side to be equals to 2 into 1 minus 1, and that is 1. Then the right hand side will be equals to 1 square, which is equals to 1. Therefore, left hand side is equal to the right hand side. Then we conclude that the first step is true. It is true for n equals to 1. So now take the second step. Is it true for n equals to k? Plus 3 plus 5 plus dot 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 plus. For better understanding, let us consider another example. We want to prove the mathematical statement by principle of induction that 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus dot 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 plus 1 over n into bracket n plus 1 is equal to n over n plus 1. So what we need to do here is very simple. We just have to prove three things. The first step is to prove that it is true for n equals to 1. The second step is to take the inductive hypothesis that it is true for n equals to k. Then we can then show that it is also true for n equal to k plus 1. So let us start. If I have 1 over 1 times 2 plus 2 over 1 over 2 times 3, I beg your pardon, plus 1 over 3 times 4 plus dot 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 plus 1 over n into n plus 1 equals n over n plus 1. The left hand side of this mathematical statement is 1 over n into n plus 1, and the right hand side of the mathematical statement is n over n plus 1. So is it true for n equals to 1? So the left hand side of this mathematical statement will be 1 over 1 into 1 plus 1, and that is 1 over 2. And the right hand side is equal to n over n plus 1, which is the same thing as 1 over 2. So since the left hand side is equal to the right hand side, which is equal to 1 over 2, we say that it is true for n equals to 1. So we take the second step. Is it true for n equal to k? This is our mathematical statement. Wherever we have n, we just replace it with k. That will be 1 over 1 multiplied by 2 plus 1 over 2 multiplied by 3 plus 1 over 3 multiplied by 4 plus dot 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 plus 1 over, now n is k, now be k into k plus 1 equals k over k plus 1, equation 1. We take the inductive hypothesis, assume it is true for n equals to 1. Then finally, we say, is it true for n equals to k plus 1? From still on the mathematical induction, let us consider another example. in another form. Prove that for all natural number n, 5 raised to power 2n minus 1 is an integer multiple of 24. We are told to use mathematical induction. So the first thing we are given is 5 raised to power 2n minus 1. Then we take the first step. Is it true for n equal to 1? We have our mathematical statement to be 5 raised to power 2n minus 1. That will be when n equals to 1, we say 5 raised to power 2 into 1 minus 1. And that is 25 minus 1, which is equals to 24. So 24 is an integer multiple of 24. We can say it is true for n equal to 1. Now the second step, true for n equal to k. So our mathematical expression, which is 5 raised to power 2n minus 1, will now be the same thing as 5 raised to power. Whenever we have k, n, we say it is k. 2k minus 1. But since we have 5 raised to power 2 into 1 minus 1 equals to 25 minus, which is 24, we can as well say that this 5 raised to power 2k minus 1 is equals to a multiple of 24. That is 24 multiplied by m, where m is a positive integer that is greater than 0. So we now say assume it is true for n equals to k. That's our inductive hypothesis. So from this one, we see that 5 raised to power 2k is equals to 24m plus 1. Let us keep this aside. Now let us see for n equals to k plus 1. Is it true for n equals to k plus 1? We are going to have our expression, our mathematical statement to be 5 raised to power, wherever I have n, it becomes k plus 1. 2 into k plus 1 minus 1. Then we multiply with 2. That will be 5 raised to power 2 times k, 2k, 2 times 1 is 2. Then minus 1. So we apply indices here. Here will be 5 raised to power 2k dot 5 raised to power 2. That is by indices minus 1. And this is 25 multiplied by 5 raised to power 2k minus 1. However, our 5 raised to power 2k is equals to 24m plus 1. So whenever we see 5 raised to power 2k, we replace it 24m plus 1. So here will now be 25 into 24m plus 1 minus 1. From there, so by the time we expand to 25, we are going to have 25 times 24m plus 25 multiplied by 1. That will be 25 minus 1. And finally, that will be 25 times 24m. 25 minus 1 is 24. That will be plus 24. So 24 is common. You say here will now be 24 into 25m plus 1, which is a multiple